start. So waves and optics, we're gonna be speaking about visible light here. So optics really is a branch of physics where we study light and its interactions with matter. Right, so it plays a very important role in the design of lenses, microscopes, and the nature of visions, telescopes, and other technologies like lasers and fiber optics. Right, so we know that light is a form of electromagnetic radiation that travels in waves, and its interaction, right, with different surfaces and media give rise to the phenomena of both refraction and reflection. We're going to be looking at those. So let's start off with reflection, the laws of reflection. Reflection occurs when light strikes a surface and bounces off of it. It is an essential phenomenon in the study of mirrors, image formation, and optical devices. The behavior of light during reflection can be described by the laws of reflection. All right. So we're starting off here. So we looked at that here. This is fine. Okay. So the laws of reflection now. The first law of reflection, the angle of incidence, the angle between the incoming ray and the normal, is equal to the angle of reflection, the angle between the reflected ray and the normal. So theta I is equal to theta R. So let's look at that. All right, we're gonna look at that. And then the second law states that the second law of reflection states that the incidence ray, the reflected ray, and the normal ray to the surface all lie in the same plane. Right? And we'll look at what that means. Alrighty? So let's observe the first law. This is the incidence line, normal line rather. So the incoming ray will bounce off. Right? So sorry, this is the incidence ray. Right? So the green rays will bounce off of each other. And note that the angle of incident theta I is equal to the angle of reflection theta R. And notice that all the rays A, the normal, and B are all in the same plane. That is the second law. Let's have a look at this. Let's use a simple prism. Let's use light. It must be at an angle. Right? So we have something like this. Right? We're going to have the angles being somewhat the same. The reflection, rather. I want to see the reflection more so than everything else. Right? So when we look at that, we should also be able to see a normal. Right? The angle here, the angles here, the reflected rays should be the same. Alright, we're just looking at that. It should be the same. And then the reflected ones are on the same plane as well. Alright, let me see what's in here. Nothing is in here that's important. Well, is there reflections here? Nope. Alright, so we're just looking at that. Could look at it like this as well. Right? Notice that we have a rainbow being produced out of the prism that in that direction. Let's do this. Let's turn off the reflections. Let's rotate this. Notice that you guys can see a faint rainbow. Let me take this and rotate. Let me rotate this as well, so the normal can allow it to spread downwards a little bit. Hold on, I want it to go that direction. All right, so we can see like a rainbow coming out. If we want to see it a little bit better, we can scatter the light a little bit more using a concave lens, and now you can see the rainbow a little bit more. Right, so this is a result of something that we call refraction. Right, and we're gonna be looking at refraction a little bit more, but we're just focusing on the principle of reflection first. All right, so the reflection that we're looking at, right, we just need to know. Let me put away this because that's not necessary. Right, when we have a reflective ray, this is the reflective ray now. So this is the incidence ray and the reflective ray. Right, the angle of the incidence, or the angle of the incident ray to the normal, is equal to the angle of the reflected ray rather to the normal. So that is the law of reflection. But for refraction now, we have the first law of refraction, otherwise known as Snell's law. When light passes from one medium to another, the ratio of the sines, right, of the angle of incident and the sine of the angle of refraction is constant and is equal to the ratio of the refractive indices of the two media. Sine theta I over sine theta r is equal to n2 over n1. n1 is the refractive index of the first medium and n2 is the refractive index of the second medium. The refractive index is found by taking the speed of light and dividing it by the velocity, right, of the speed of light through that medium, right? So it's something like that. So refraction like this occurs. Why? It tends to occur because as light travels from one surface to another, or from one medium to another, the light speed changes. So the speed of light changes and different wavelengths of light travels at different speeds, right? So we're going to, wait, let's hold that there because I think I jumped the gate a while ago, right? But it bends because it slows down or it speeds up through a medium, right? So they will slow down and it will cause bending as it slows down. So how does refraction occur? Why does refraction occur? As light moves from one media to another, the speed difference causes refraction. The speed difference causes refraction, all right? So let's look at this. For example, we can look at this here. So we have diffraction there, right? Where we don't have one straight line here, but we have it bending at an angle to the normal here. So an incident angle and a refracted angle. I'm wondering if I can write on the simulation. Yes, I can. So I have an angle of refraction right down here, this theta, angle of refraction. I have an angle of incident here. All right, so we have that there. So remember, it is dependent also, right, on the refractive index of a material. So the refractive index of a material really and truly shows us how much light slows down, right, in that media. So if I were to switch the refractive index of water, which is roughly 1.33, and carry it closer to glass, you can see that that angle shrinks. The angle shrunk. Because a different refractive index will give you different angles of refraction. The light will not diffract, or the light should not diffract in air. For example, if I need to erase this, will not diffract in air. For example, if I do something like this, hold on, let me change from the pen. If I do something like this and shoot the light off, we know that the light will not bend because the medium has not changed. The refractive index of air will always be 1.0003, or roughly 1. It is only when it passes into a media, right, at an angle to the normal, that some bending happens. Notice when it's at no angle to the normal, here the normal remains the same. But when we refract it, when we shine the beam at an angle now, we end up with the bending here. Alright? And we're also saying Snell's law, sine of the incidence angle over the sine of the refracted angle is equal to n2 over n1. n2 in this case will be glass. The glass square that I have here. N1 will be the refractive index of air. So we could test this out. And I'm going to test this out for you guys to see Snell's law in action. Alright? So if you were to get a protractor really, and measure the angle of incidence here, that is roughly 670. That's roughly 70 if we were to take down that value. Right? let's say that's roughly the angle of incidence is roughly 70. Let's erase all of this off of the screen. Let's say that theta I is roughly 70. My bad, right? And if we were to rotate now to find the angle to the normal for the refracted one now, let me change this to find that angle there. Well, it would be better if I do something like this, right? That is around 30 something, right? Obviously, this won't be perfect. That would be 30 something, right? So it's saying now that sine of 70 over sine of 30 should give you something roughly equivalent to the second medium, which is glass, right? What would be the refractive index of glass? Let me go back to this simulation and see what the refractive index of glass in this experiment is. All right, so let me just go back. On this simulation, what is the refractive index of glass that we have here? 1.49, right? So technically, this should be equal to 1.49 divided by the refractive index of air, which is 1.0003. So if we were to calculate this now, hopefully this doesn't go terribly wrong, which it can, right? So sine of 70 divided by sine of 30 is going to give us 1.879, right? And 4.9 divided by 0.0003 should give us a completely different value, which is around 4.898. Right? So what's happening here, right, is deviations due to generally the experiment, etc. Right? But if you continuously tweak and try to get the perfect angles, the law should in theory work. Right? So that's how it works, right? Earlier this morning, actually, I did it and got the exact value, and that was from taking a couple minutes to try to sit down and read where the exact angle is, but nah, that is something that I will not do now. But yeah, so Snell's law, right? So remembering Snell's law should be the sine of the angle of incidence divided by the sine of the angle of refraction is equal to the refractive index of the second medium divided by the refractive index of the first medium, right? So the second law of refraction now, it's the same thing. It is the same thing that I discussed before. That when light enters a different medium, it will bend. Why does it bend? Why does it slow down? When light enters a denser medium, such as air to water, it slows down and bends towards the normal line. So that is going to be very important when you're looking at refraction, right? So it will always bend towards the normal line, and it always occurs when it moves from a medium to a denser medium, right? So less dense to dense. If it moves from denser to less dense, then it will bend away from the normal line. And that is what the second law of refraction is stating, right? So if it is less dense to dense towards the normal line, right? Denser to less dense, it is away from the normal line. So it's how the light bends, right? So we could look at that in another PhET simulation to figure out how that really works. Just loading up the simulation right now so you can see what occurs here, right? It's around the same simulation, more or less. So the material, the starting material we have is air to glass, right? So the glass has a refractive index of 1.5 in this case. Therefore, it will bend towards the normal as air is less dense, right? But if we switch this around and make this glass, right, and make this the air, we see that, well, let me put it back first so we can have a line to look at, right? So I want us to show that it actually has bent away. So let's put a line here. This is the initial angle that we have here, this initial angle here. All right. So we're working with that. If we were supposed to change what we're working with now, so change this to glass, right? And then change this down to air, we see how, what's happening here. Air, it doesn't, hold on. The index is a bit too much. All right. So I can't make it exact. I want it to be close enough to air as possible, right? So it has to be somewhere around there, right? So the angle will now bend away. So we see that we have a new angle that has been bent away. So why it didn't escape a while ago is actually what we call total internal reflection when we have a critical angle, right? Because it's at 90 degrees. So it's a critical angle we hit a while ago. And that is going to be the essence of the next thing that we will discuss in optics, right? Which is total internal reflection, all right? But really and truly, that's what reflection and refraction are all about. You just need to understand their two laws, right? And that is about it. All right? Any questions or concerns before we move on to total internal reflection? Yes, no, maybe. Alrighty. So total internal reflection, right? So as you can see from this, right, we have reflection that occurs over and over again within a medium, right? So it occurs when light rays travel through a denser medium, strikes the boundary of a less dense medium at a sufficiently large angle, for example, a 90-degree angle, right? So when it strikes at a sufficiently large angle, rather than refracting into the less dense medium, right? The light will completely reflect rather, back into the denser medium. This principle is crucial for understanding how we operate things like fiber optic cables, right, and different sorts of other optical devices, right? So we're gonna be using fiber optic cables as our main example, right? But this is really total internal reflection, right? So we have a less dense light moving from a less dense medium to a more dense medium. Here we're focusing on this diagram, right? At 0 degrees, right? At 15 degrees it can refract. At 30 degrees it can refract. At 45 degrees it can refract. But you see at this 45 degree, it does not refract out, but it reflects totally inwards. That is what we call a critical angle, right? And that is what we call total internal reflection, right? So the critical angle is the angle of incidence in the denser medium, for which the angle of reflection is less dense. In the less dense medium becomes 90 degrees, right? So what we're talking about is the angle of incidence in the denser medium, for which the angle of refraction in the less dense medium becomes 90. And this angle of reflective light travels along the boundary between the two media, alright? So we're going to be looking at the critical angle completely. So from Snell's law, we have this rearrangement, right? Where we just multiplied both sides by n1 and we end up with this, right? So we have n1 sine the first angle equals the second sine of the second angle, right? And the critical angle, right? So we're not looking at the first medium, notice that we don't have any n2 because we're focusing on the first medium alone, right? The critical angle theta c occurs when the angle of refraction theta 2 becomes 90. So let's assume theta to be 90. Therefore, Snell's law simplifies to n1 times sine of the critical angle is equal to n2, right? Is equal to the refractive index of the second medium, right? So solving for the critical angle now, we will take the inverse side to get the critical angle, and that is the formula of the critical angle. All right, so that's what's happening for Snell's law. right? That's derivation. So the critical angle is equal to the inverse sine of n2 over n1. That is it. Any questions or concerns before we move on? So that's what we're working with. Danielle, Jamelia, Videsh, Celia, are you guys okay? Christine, Martiva, the person called S. Are you guys okay so far? You guys are fine? Okay. So working with the critical angle there. The next thing that we're looking at is fiber optic cables and how we actually use total internal reflection, right? So we know that these fiber optic cables are actually a perfect example for this, right? Because it uses light signals, right, to transmit data through these cables, right? So they tend to have a glass interior. So what happens here now? This is how it works, right? So the light enters the core, right? And light is injected into the core of the fiber optic cable at an angle here, right? And then because we have ejected it at the critical angle, it will continue to travel to these angles, right? And continue to become, well, continue to be reflected, right? Internally reflected in the cable until it reaches the receiver, right? When it's done like this, due to the total internal reflection, the light signals remain confined within its core and we have minimal loss of signal strength. So we have stronger signals due to these fiber optic cables because most of the signal is maintained because everything is kept within this area, right? Through the total internal reflection, right? So it allows for large amounts of data, right, to be transported. So this is how people's telephones, right, your internet, your television signals are traveling at a high speeds. So yeah, so it requires you guys to well, it requires, right, not really, that's not the word I'm looking for, but basically this allows for information to be traveling at high speeds. Alrighty. Another natural implication of the total internal reflection now is mirages, right? So the air, right, down here is less optically dense, right? And the optically denser part of the atmosphere is a bit higher, right? So when the sun's rays actually travels through, right, it actually goes at different angles and refracts at different angles, and sunlight actually undergoes the total internal reflection, right? And it actually causes, right, the viewer to trace backwards and actually see light, right, on as if it were on the ground. So we tend to notice the sky, right, the blue sky as if it were on the ground, and it creates what we call a mirage. So for example, in actuality, this actually happens, or you guys can probably think of it more likely in cartoons where you can see a huge lake in the middle of a desert, right? But really and truly, it's the light from the sky, from the sunlight, refracting, right, into the view of the viewer, right? Basically into the path of the viewer, and they perceive it as this light being on the ground. So it creates this optical illusion, right, of a mirage. So that's what's happening there. So for example, here we see an optical mirage under this bridge as it is reflected in here, right? Or we're just seeing our reflection, right, in here, right? So a general reflection of light. So this was just something to sum up, right, and to sit and see if I can answer questions too, right? But we are more or less done with the principles of optics, and next thing we'll go into is the introduction to lenses, right, and focal length. Right, so lenses are next.